so far we've defined our rotational motion variables, and we've also seen that angular displacement, angular velocity, and angular acceleration have the same relationship as their linear counterparts. Our last big idea for today is looking at the relationship between linear and rotational motion. So if the linear motion has the same relationship between position, velocity, and acceleration as the angular motion, then it stands to reason that there is a connection between the linear motion and the rotational motion as well. So let's look at our object moving on a circle. Let's say it starts at the point on the right and it rotates up toward this higher point. So we know that it's gone through an angular displacement of delta theta. If we think of the linear distance the object has actually traveled to go from point A to point B here, we can trace its path and we can see that that is the arc length. And so we've previously defined, well, the arc length is that angular displacement times the radius. So the actual linear distance in meters is the angular displacement in radians times the radius in meters. And so if you notice, the radians kind of just disappears and meters takes over as our unit here. All right, let's look at what's happening with our velocity. So at a given moment, we know from our circular motion that the object is moving tangential to the curve. And we also know from early kinematics, velocity is displacement over time. So velocity is s over t, and s is delta theta over t. Sorry, delta theta r is s, and then we're dividing that by t. I'm just going to separate this out a little bit to show a relationship, a trend we're going to be seeing. Delta theta over t was our angular velocity. So the linear velocity is equal to the angular velocity times the radius of the circle. And so this outside edge, this is the main part you need to know. And they have added it to the formula sheet this year, so it's not something you have to memorize anymore, and it is going to be super helpful to know that relationship. There is one more kind of interesting point about this tangential velocity. So it is dependent on the radius. So that means if we're looking all the way on the outside edge of the circle over here, that's not going to have the same tangential velocity as a point closer to the center. So at different radii, the velocity is not constant. But the angular velocity is constant. Because if you think of this disk rotating, it's a fixed object, which means all points along that are rotating together. They're not bunching up and moving around as it rotates. So omega is a constant because the object's rotating at the same rate. I'll say omega is the same at different r. because it's rotating at the same rate. All right, so the tangential velocity does depend on the radius. The angular velocity does not depend on the radius. All right. I guess I'll add on to my drawing up here too. So this is our linear velocity, our tangential velocity that I've already drawn. We also have omega, which is showing, how much this is rotating per time. All right, last relationship here. We also have a linear acceleration called the tangential acceleration. And that is, how the tangential velocity essentially is changing at any given moment. So from previous definitions, acceleration is delta v over t. And so we know v is omega r, so delta omega r over t. Kind of pulling things apart the same way we did before. So delta omega over t times r, and that is our angular acceleration times the radius. So again, the linear acceleration also depends on the radius. We'll mention too, the tangential acceleration changes the velocity, the tangential velocity's magnitude. That didn't need the apostrophe. Changes v's magnitude. So it could actually be speeding up or slowing down. The rotation could be speeding up or slowing down. Now, previously with circular motion, we had looked at one more relationship. We had a very special type of acceleration that kept our object on a circle, and that was our centripetal acceleration. And it's called centripetal acceleration because it always points toward the center of the circle. We still have that. We can still consider that for rotational motion. If y'all remember, centripetal acceleration was v squared over r. This is our tangential velocity. And of course, r was our radius. And you can think of, what this did. This kept the object on the circle. So we can think of this as changing the velocity's direction. So we have two different types of acceleration. Do keep them separate. We have our tangential acceleration is directly related to the angular acceleration alpha. So is the rate at which it's spinning speeding up or slowing down? But then we do also have centripetal acceleration, which keeps our object on the circle. It points toward the center of the circle.